Hello everyone, my name is Erica Avery and I have prepared this PowerPoint presentation in regards to relative risk, odds ratio, and rate ratio. Relative risk. Relative risk is one of the most intuitive measures in epidemiology. It is used to describe outcomes associated with predictors, or exposures, evaluated in RCTs and cohort studies. Both are retrospective and prospective studies. In general, the relative risk may be used anytime there are data that follow exposed and unexposed persons forward in time to assess for the outcome of interest. Odds ratio is a measure used to describe associations emerging from case control studies. They use the same notation within the 2x2 table to describe it. This table is used to describe frequencies of data. This design is key to their analysis and interpretation. However, to use an example that is set up as a cohort study, as we have done previously, would be inappropriate. Measures and designs are integrally related, and it is not correct to change one without changing the other. Rate ratios are closely related to risk ratios, but they are compared as the ratio of the incident rate in an exposed group divided by the incident rate in an unexposed, or less exposed population comparison group. An example of this would be the number of events over person time. And we'll get more into that in just a few slides. Risk, odds, and rate. Risk is the number of events over population at risk. The difference of risk to odds is in the denominator. Risk has the disease and non-diseased, or everybody. It is important to know that odds is the number of people with the disease out of the number of people without. So it would literally mean probability of the event of people with the disease out of the number of people or the event without the disease. Just a side notation, in the denominator of this rate, the probability of the event not occurring would be in the denominator and not the total as we've seen in risk. In order to find rate, we need to figure out how long each of these people were at risk for developing the disease, so the formula would be the number of events out of the population at risk per unit person time. Or we could use an alternate formula, risk out of the number of people, time period at risk. This summary of definitions is just to highlight an easy chart to review over the information we just reviewed in the previous slide. Again, in our measure column, we can see we have risk, odds, and rate ratios. Again, we have the formulas depicted here for us, which we had just gone over. And in the range and important values field. I did just want to highlight in this bottom one for rate. I know we went over the number of events out of person time. However, we must remember when we're calculating this, it is calculated as person multiplied by time. So when we go through our work assignment, we'll go through and explain how this is calculated. Relative risk, odds ratio, and rate ratio. Again, this brief slide is just here to highlight that all three are ratios. They could be between 0 and 1, could be 1 with no association, they could be greater than 1, and they will never be negative. So we'll just keep these in mind when we are calculating for our assignment. Understanding the 2x2 table. The above 2x2 table is an example from this week's assignment. You will notice the alphanumeric characters for each column. This will help us plug in the appropriate numbers for our formulas when searching for a desired outcome or result. This table is constructed from information provided on research and findings, which discusses those affected or exposed and or those not exposed. This can also be the case for when those with the disease and without. Again, this is relative to our course assignments and instructional videos where we discuss those who have been exposed among those without, and we'll get more in depth with that in just a few slides. In these next few slides, I just wanted to highlight some simplified formulas for our assignment in regards to risk ratios. This one for relative risk, we are using the formula where we have A out of A plus B divided by C out of C plus D. I know right now this doesn't look comprehensive, but as we move forward, we'll understand what we have for our populations and these alphanumeric characters and why they're set up this way. So we'll move forward and show you a couple more simplified formulas, and then we'll plug these in and explain. Our odds ratio, we have a couple different formula options. We'll use A out of B divided by C out of D, or number of events, and we'll go through this again as I was mentioning in the previous slide for upcoming ones. The alternative formula we can use that's not too common, some students may decide to use this, is A multiplied by D divided by B multiplied by C. And again, we'll explain this. Our rate ratio, one of the formulas we can use is the incident rate, or the first incident rate, or occurrence, over our second incident rate, or group. And this will make more sense once we have information we can plug in here. Where incident rate is the occurrence of an event over person time, for an example, person years. And we will see something very similar to this language in just the upcoming slides. Another alternative we can use is the incident rate, which is events over person time. Discussing the use of odds ratio to approximate the relative risk. What is the relationship between odds ratio when using to approximate the relative risk? The odds of an event is the number of events out of the number of non-events. This turns out to be equivalent to the probability of an event out of the probability of a non-event. Again, we're using this formula here where it's the odds of an event in a treatment group out of the odds of an event in a control group. So you can go ahead and see here where we have our exposed and unexposed populations. And again, it's among another group here. And then we'll plug this in with our work we've been assigned this week. So you'll see that. Continuing in correlation to our last slide, let's compare this to relative risk, which is the probability of an event occurring. And we have an example here, which is A out of A plus B out of the probability of the event not occurring, which we see here, which is C out of C plus D. They both measure association between a binary outcome variable and a continuous or binary predictor variable. So once again, we see it set up where we have the risk of an event in the treatment group out of the risk of an event in the control group. And this is the formula we will use to calculate this. To conclude the importance of using odds ratio to approximate relative risk, we will use our odds ratio calculations prior to utilizing our relative risk formula. So it's important to follow these step by step, understanding which ones to use first to conclude our data when using the last relative risk formula. Let's not forget, continuing off our last slide, sometimes it's not possible to survey large populations and collect data on the number of cases. This is particularly true with rare outcomes. Case control studies are used to study these situations. Descriptive measures used are odds and odds ratio, which can approximate the risk and relative risk, as we were mentioning in the last slide. Measures in action. Here's what we were given. For each city, we are going to calculate the risk, odds, and rate of stomach cancer among heavy drinkers and non-heavy drinkers. Next, we will calculate the relative risk, odds ratio, and the rate ratio for stomach cancer among heavy drinkers as compared to non-heavy drinkers. Please note the use of the odds ratio will be utilized to approximate relative risk in the following slide. So I did just want to attach this example from our homework assignment. That way we can get a clear picture of what we're using and where we're getting certain numbers for those that are heavy drinkers with stomach cancer, those that are heavy drinkers without stomach cancer. Just to give you an idea, and same thing here, those that aren't heavy drinkers that do have stomach cancer and those that are heavy drinkers that do not. And so we do have two different cities here, Atlantis and Camelot. So in the next slide, we will go through and explain some of our calculations and required information we've retrieved. Okay, so on this slide, we have our assignment and calculations. Again, as I was mentioning, we do have the imperative information we've pulled from our last slide in regards to the city of Atlantis and Camelot. So the risk of getting cancer, the population we're evaluating is the heavy drinkers. So we used 18 of those that were heavy drinkers out of the total population. So again, for risk, remember we're using the number of events out of population at risk, which gave us the total number here. And very similarly, we used the same, again, number of events out of population at risk. Same formula was used for the non-heavy drinkers. This is our population this time. So the rate, again, for risk is the number of events out of the total population we were given. And again, the same for Camelot, the number of events out of the population at risk. For odds, we were given a population of heavy drinkers. So for this one, we're going to be doing the number of people with the disease out of the number of people without. And we're going to use this formula for both Atlantis and Camelot. And again, the same formula is going to be used for our non-heavy drinkers for Atlantis and Camelot. The rate of cancer is the number of events out of a population at risk per unit person time. So you can see we did it based on the heavy drinkers population, and we did it for Atlantis and Camelot. And again, the same formula was used here for non-heavy drinkers for Atlantis and Camelot. The relative risk for getting cancer. For this formula, we're going to use the one we were given by our 2x2 table, where it's A out of A plus B divided by C out of C plus D. So with the help of this formula, we've plugged in our numbers, and this is our answer. And again, we're using the same formula here to get our answer right here. Odds ratio for getting cancer. So the population we were given is heavy drinkers compared to non-heavy drinkers. The formula we're going to be plugging in here is A divided by B out of C divided by D. So we're going to use, again, information from our 2x2 table, plug in the information, and this is the answer we end up getting for Atlantis. And again, for Camelot, we're using the same formula, and this is the answer we end up getting. So rate ratio for getting cancer. Our population is heavy drinkers compared to non-heavy drinkers. So for this formula, we're using the events out of person time. So we were using what we previously solved and plugging in. So you can see here, we're going to be using the events out of person time. And this gives our answer here for Atlantis. And very similar, again, we're using the events out of person time. And here is our answer. I want to thank you for taking the time to review and listen to this lecture.